Okay, so we will now be moving into the Renaissance. So there was a greater need for math due to complex business structure, which led to a new group called the Abbacists, which came about in the 14th century. They taught merchants the decimal system and they had advances in the use of symbols. We also have during this time Dardy's cubic equation. He was able to look at this by completing the cube. We also have Stafel, who worked with negative powers. And during this time, there's printing of books, and here we see that the first English algebra textbook was written, and I have a picture of it right here. Also, in the 1500s, Del Ferro discovered a solution to the cubic equation. We also have Cardano, who would later publish the solutions. We have Bombelli, who used imaginary numbers, and as well as Vieta, who used letters for known constants. Okay, moving on to trigonometry. So they were able to use math and art. We see a picture here of the Last Supper, and they use perspectives, the geometry of perspective, to kind of see depth and put more depth into the art, make it almost make a 2D image look three-dimensional. We see that here in the Last Supper. Okay. We have Regent de Montes, who wrote the first trigonometry text, which proved the law of sines. We also have Rheticus, who defined trig functions based on triangles, not circles. And we have Simon Stevin, who argued for decimal fractions. And today, people typically like to work more with decimals because it's more easy to tell what the value is. Sometimes fractions are a little more complicated. Okay, now we'll be moving into logarithms and astronomy. So we have here that John Napier published the first table of logarithms. Now his logarithms were a little bit different than the ones we see today. Our more modern version of logarithms comes along with Henry Briggs, who constructed the modern law table with base 10. Okay, moving on to the astronomy side of things. So during this time, there was a realization that Ptolemy's predictions about astronomy were not completely accurate. We have some new findings right here. We have Nicholas Copernicus, who believed that the Earth moved around the sun. We also have Kepler, who realized that the orbit was an ellipse. And so we see right here a picture of it, and we see the planet is moving around the sun in an elliptical pattern, and that the sun is at one of the foci of the ellipse. We also have Galileo Galilei, who defined uniform acceleration. He also did some work with projectiles, and he was able to determine that 45 degrees was the angle that you should shoot something if you want the maximum range with a projectile. Okay, moving on to 17th century algebra. We have William Agregard. He used algebraic equations to find unknowns. We also have Thomas Harriot, and down here you see a picture of a person making a map. Thomas Harriot was actually a cartographer, and that's what cartographers do, was just make and draw maps, and so he had that background coming into it. And he understood the connections between roots and factors. And we also have that vowels were unknowns and that constants were known values. Okay, we have Albert Gerard, who introduced factions and used them to connect roots and coefficients and developed the fundamental theorem of algebra. From this, we can take away that the number of roots equals the degree of the polynomial. Okay. Okay, moving on to analytic geometry. We have Pierre de Fermat. He found that two variable polynomial problems will give a line or curve, and if the power is less than or equal to 2, it will be one of Apollonius's conic sections. Okay, next we have René Descartes. He used curves to create equations and credited for the Cartesian coordinate system, which you see down here. We also have John DeWitt. He was the first systematic algebraic treatment of conics. Okay. Okay, moving on to 17th century probability. We look at first at Pascal's triangle. He was the first to use mathematical induction. So he had a base case, and then he proved that it stood true for n minus 1. And here we also have Pascal's triangle. So this is looking at combinations. And so we're moving down this triangle. A trend that we notice is that the sum of the two above equals the one below. So we have 1 and 3, 4, 1 and 4, 5, 4 and 6, 10. That's just something to note. Okay, we also have Huygens, who dealt with problems of expected value. And we also have Fermat, who made contributions to number theory and used method of infinite descent. Okay, moving on to calculus. Now, they looked at calculus from a little bit of a different perspective. The main thing they saw with calculus is that they were able to connect tangents. They looked at the tangent lines for everything. And so you see here, Fermat was able to find extreme values as well as the idea for finding tangents. Okay, we have Descartes, who found the circle is normal to a circumference and a circle radius is normal to the curve. And next we have Cavalier, who broke up areas into smaller regions under the curve called indivisibles. And that's actually what I have a picture of here. And so when they thought of area, they wanted to approximate it. And so they looked at finding the area of rectangles under the curve. And we see here that this would actually be an over approximation because we have the corners of the rectangles are above the curve, so we're calculating that as well. So we're going to get an area a little bit higher than what we want. Okay. We also have John Wallis, who found areas under the curve for y equals x to the p over q over interval from 0 to 1 using indivisibles. And his main focus was on the area of a circle. That's what he focused on. Okay, and we had 3 different people who started contributing to the fundamental theorem of calculus. And so they didn't look at it as antiderivatives per se, but they looked at it from connecting tangents and areas instead. So when we think about the fundamental theorem of calculus, it's really antiderivatives, but they had a little bit different way of looking at it. Okay, and I believe that is it.